So today we're going to talk about definite integrals, which means we're transitioning out of our limit definition of Riemann sums and into finding actual values using integration methods. So to recap from 4.1, we talked about indefinite integrals, where the answer is a function, so some sort of expression, plus c, this unknown constant. And so if I want to find the integral of 3x squared plus 4x minus 8 dx, then I would say this is 3x to the third over 3, so x to the third, plus 4x squared over 2, so plus 2x squared, minus 8x plus c. That's the indefinite integral. It's also known as the antiderivative. And that means that you can check your work. If you take the derivative of your answer, you should get the expression in the integrand, or the thing that's in the integral. So we're going to link up this process, how to come up with these terms for indefinite integrals, to evaluate definite integrals. But in 4.2, we were just approximating definite integrals using Riemann sums, or we were finding the exact values of definite integrals, but it was sort of the long way based on that limit definition. So for Riemann sums, if I want to set up an approximation for the area under f of x equals x squared on the interval 1 to 3, I could use 4 equal subintervals and get an approximation. These look like they are, it's an upper sum, or they're right-sided endpoints. So this would be an overestimate. So this one will be, well, the integral from 1 to 3 of x squared dx is approximately equal to, let's see, the width of everything is a half unit, right? Because delta x would be 3 minus 1 over 4 subintervals. So each rectangle has a width of 1/2. And then the function values are the function values on the right. So f of 3 plus f of 2.5 plus f of 2 plus f of 1.5. Right? That would be the setup for that area. We're not going to calculate the area. I'm just reminding you where we've been. This wouldn't be the exact area. It would be an overestimate, because I can see that this function is increasing, and we did a right-sided sum, so that's an upper sum, which is an overestimate. If we use the limit definition, we can find the exact area under the curve between 1 and 3, because we're not going to be using a set number of rectangles. We're using an infinite number of rectangles. So this would be the integral from 1 to 3 of x squared dx is equal to the limit, as n approaches infinity, of the sum from I equals 1 to n. In general, it's of delta x times f of xi. And then remember, your job is to figure out what expression is delta x and what expression is f of xi. So off to the side here, delta x is 3 minus 1 divided by n subintervals. So it's 2 over n. And f of x sub I, our function is x squared, something squared. It always starts at the beginning of the interval, which is 1. Add to that delta x times I, and then substitute in for delta x, 2 over n times I, and then it's worth your while to go ahead and square that out. 1 plus 4i over n plus 4i squared over n squared. So we're not going to go through the entire evaluation process, but I am going to write this out. The limit as n approaches infinity of the sum from the first term to the nth term of 2 over n, that's delta x, times 1 plus 4i over n plus 4i squared over n squared. The next step would be to distribute the 2 over n through, take the summation, meaning use your three rules to figure out the sum of each term, and then take the limit as n approaches infinity. All right, this would not be an estimation. This would be the exact value. All right, so let's do one full limit definition here. Evaluate the definite integral from -2 to 1 of 2x dx. So delta x, we're on the interval -2 to 1, so it'd be 1 minus -2, which is 1 plus 2 over n, so that's 3 over n. And f of xi, the function is 2 times x, so 2 times something. Our interval starts at -2, and then we add to that delta x times I. And then we sub in what we know. 2 times -2 plus 3 over n times I will be 3i over n. Might as well distribute the 2, so -4 plus 6i over n. So the integral from -2 to 1 of 2x dx is equal to the limit as n approaches infinity of the sum from I equals 1 to n of what? It's delta x. Now I'm going to, normally I write delta x f of xi. I don't want to write a whole nother line, so I'm going to jump right into it. Delta x is 3 over n, and f of x of I is -4 plus 6i over n. Keep the limit notation. You really should be able to distribute and drop your sigma notation at the same time. So first I distribute. I get -12 over n. And then remember, when you add up a constant, n constant terms, you get that constant times n. It's easy to forget to do that. Plus 18 over n squared. And then when you sum all of the terms from 1 to n of I, that equates to n times n plus 1 over 2. You can clean this up if you want to in a separate step, or you can take the limit. The limit of -12 as n approaches infinity is still -12. And the limit of 18n squared over 2n squared, since that's a tie, becomes plus 9. So our area under the curve is equal to -3. And that's an exact area, it's not an approximation. Now we got a negative area because if you think about the graph of this function, it's a line, right? At -2, we'd be down at -4. Goes through the origin. And then at 1, you'd be at 2. So this makes sense because the negative area is larger than the positive area. And when we're talking about integration, we're always talking about the area between the curve or the graph and the x-axis. So it makes sense that that net area is -3. Let's make a note here. That is net area. Okay, on to the next page. Oh, oops, I just explained this down here. So we just got a negative answer for a definite integral. Is that okay? How did that happen? Yes, it's okay, because integrals are not really a total area, even though every time we've been interpreting our answer, you'll see some of my keys say change in distance or change in population, but sometimes it'll say total distance or total population. Up to this point, I think almost all of our functions have been above the x-axis. So it could be thought of as a total area. Really, integrals are net areas. So Riemann sums, whether you're talking about the definition, the exact sum, or the approximation, and definite integrals can be positive, negative. They could be 0. If f of x is greater than 0 on AB, then that area that you're talking about, the area is going to be positive, greater than 0. If the entire function is less than 0 on that interval, then that area that's below the x-axis is negative. The area will be less than 0. And a Riemann sum could be 0 if you have part of the function above the x-axis and then an equivalent area below. I drew mine symmetric, but again, it would just have to be that the net area comes out to 0. So I'm going to say net area equals 0. So our big idea here is that a definite integral, meaning an integral that has these little boundaries, like from 1 to 2 or whatever. Started talking while writing. It's always bad. A definite integral is always equal to a net area. Or if you want to think of it as a change in something, you can. Change in distance, change in population, whatever. All right, so area between f of x and x-axis is equal to the definite integral from a to b of f of x dx. It's equal to a net area, area 1 minus area 2. The area 1 would be area above the x-axis, and area 2 would be area below the x-axis. Now, don't overthink it. It's not like, well, that area is below, so it's negative, and then I get something like a1 minus negative a2. You're just adding and subtracting areas. This negative area seems bigger to me than the sum of these two positive areas, so this overall area, net area, is probably negative. All right, so what are we doing here? Starting off in chapter 4.3, we're going to evaluate definite integrals just using geometry. So instead of always using that big limit definition, which gets pretty long, if we can, I think I did this once in a textbook assignment, if we can just find the area because we have a geometric shape that we have a formula for, like a triangle, a rectangle, a half circle, something like that, then we don't really need integration methods or Riemann sums. So if I want to evaluate the integral of 2x dx from negative 2 to 1, I can just find the area of these two triangles. So the integral from negative 2 to 1 of 2x dx is just going to equal, the first triangle has a negative area, so negative 1/2 times its base, which is 2 units, and its height is 4 units. 1/2 times 2 times 4. Plus, this other area is positive, so plus 1/2 times a base of 1 times a height of 2. So I'm getting negative 4 plus 1. Negative 4 plus 1 is negative 3. And that is the answer we got when we used that limit definition to find the area. So it would be a good idea to sketch these graphs before you just jump into the answer. So off to the side here, I'm going to sketch each little graph. I have a constant function, height of 4, that goes from 1 to 3. So its height is 4. It would be like a little segment like this. So we're looking at the area of a rectangle. I don't need any fancy formula for that. It's positive. I can see the base has a width of 2. Height is 4. 2 times 4 is 8. All right, for part B, I need to graph the line x plus 2 on the interval 0 to 3. When you plug in 0, you get 2. When you plug in 3, you get 5. The area of interest is this part down here. This is a trapezoid, so I need a trapezoid formula. It's a positive area, so 1/2 times the height, which is 3, times the sum of the bases. The short base is 2 units, plus the long base is 5 units. So 3 times 7 is 21. This is 21 over 2. All right, part C. Oh, this is kind of a weird graph, right? We're going from -2 to 2. At -2, if you plug that in, you're going to get 0. 4 minus 4 is 0. Same thing at +2. And if you plug in 0, you're going to get square root of 4, which has a height of 2. It's a square root function which curves, right? And so if you haven't seen this before, functions where it's the square root of something minus x squared, it's going to look like a half circle. This half circle has a radius of 2. So this is equal to 1/2 times the area of a circle, pi times r squared. Half of 4 pi is 2 pi. All right. The integral from 0 to 3 of x minus 1, that's a linear function. If I start at 0, I'm at -1. And then when I plug in 1, I hit 0. That's important to know because you need to know where that little negative triangle is. And then we're going out to 3. When you plug in 3, you get 2. My picture's not, scaled very nicely, but the areas that we're looking for are these two. I can visually see that the net area is going to be positive. And to figure it out, I need to pay attention to which area should be negative. So the negative area is the first little rectangle. So I'm going to write it as -1/2. Its base is 1 and its height is 1. Plus the other triangle is positive. 1/2 times, this one goes from 1 to 3. So its base is 2 and its height is 2. So -1/2 plus 2 is 1.5, or 3 over 2. All right, let's talk about some properties of integrals. So let's say we're given the integral from a to b of f of x dx, and we're assuming that a is less than b, meaning these numbers aren't backwards. We're going from 0 to 3, not 3 to 0. So if a equals b, then delta x would have to equal 0. So that means that the area would have to equal 0. Because if you think about that, this is just saying the integral from a to a of f of x dx, if those two values match, then that would be 0 because there is no section to color in the area under the curve. If a is greater than b, then we would have a different delta x formula. It would be a minus b over n. But really, here's all that means. We're used to saying, okay, a is a bigger number. You know what? I want to use numbers here because I think that'll be more clear. So if a is bigger than b, let's say we're going from 3 to 0. 3 to 1. Make it something non-zero. Of f of x dx. That's backwards. We don't like that. What we want to do to be able to switch these so that they're correct is to say negative integral from 1 to 3 of f of x dx. The order of the integral matters because this formula for delta x, normally delta x is b minus a over n. Well, if a is bigger than b, my delta x is going to be negative, right? If I do it this way, then I get 1 minus 3 over n is -2 over n. So the reason this negative sign comes out is because, remember, delta x is in the formula. It's delta x times each f of x sub I. So if I'm going to flip the order around here, in order to keep that negative piece in there, I've got to put a negative symbol in, right? Basically, if your limits of integration, or what these are called, limits of integration, if they're what I consider to be backwards, then you flip them so they're going the right way and throw in a negative sign. If this was already negative, then you would make it positive. All right. let's think about this next one. We had this in one of our examples where our constant was 4. If you have the area from A to B of any constant function, the area is going to be the distance between A and B times the value of C. So it's going to equal C times B minus A. I said B minus A because I'm assuming B is larger than A, by the way. If you have a constant with an f of x, this is just a rule. You are allowed to pull the constant out in front. We talked about that with indefinite integrals too. So it's still the same even with definite integrals. And if I have the sum or difference of two definite integrals, I am allowed to, or of two functions, I'm allowed to split that into the sum or difference of two definite integrals as well. And when I do that, I've got to make sure I put dx's on both of my integrals. All right. Now this next one is kind of weird because there's nothing written next to it. But let's add something to this. Let's say we have some value c that falls between a and b. So maybe a is 0, b is 3, and c is 2. If it's helpful, which it will be in some problems, you are allowed to split this integral into the sum of two different integrals, or we're thinking like net area here. We could say the integral from a to c of f of x dx plus the integral from pick it up at c and end at b of f of x dx should be equal to whatever the integral from a to b is. You're just breaking it into pieces. It's sort of like, here's the area of the small triangle, here's the area of the big triangle. We were doing that back here without using official integration language. And then finally, if f of x is greater than or equal to 0 on this interval, then the area under the curve, the integral from a to b of f of x dx, is also going to be greater than or equal to 0. And if f of x is greater than or equal to some other function g of x from a to b, then we know that the area under the curve of f of x should be greater than or equal to the area under the curve of g of x. Right? Because this is just saying, here's a visual for this one. Here's f of x. Here's g of x. If we're looking at the same a to b, f's area is all of this, which is larger than g's area, which is just this part. If they're equal to each other, then their areas are equal. There's no way that g of x could have more area than f of x, even if g of x is way down here and it's got all this area. Remember, that's a negative area. So that's smaller than whatever f's positive area is. All right, practicing just a couple, evaluating integrals using some of these properties. So the integral from pi to pi of sine x dx, you shouldn't have to plug anything in. You don't have a range of values. You're looking at the same value. Pi to pi should be equal to 0. The integral from 3 to 0 of x plus 2 dx, that's backwards. We want to straighten it out by saying the negative integral from 0 to 3 of x plus 2 dx. And this seems familiar. Did we do this one? We sure did. Part B on the previous page, we found that the area from 0 to 3 of x plus 2 dx was 21 over 2. So this one should be negative 21 over 2. If I didn't find that earlier, I would do negative parentheses and then figure out what that area was and just make it negative from there. All right, and then given that the integral from 1 to 3 of x squared dx is 26 over 3, and the integral of x dx is 4, the integral of just dx itself is 2, I want to figure out what is the integral of negative x squared plus 4x minus 3 dx. This is without using integration techniques, using just what I'm given right here. All right, so we can split this up. This is equal to the negative integral from 1 to 3 of x squared dx plus 4 times the integral from 1 to 3 of x dx minus 3 times the integral from 1 to 3. When I pull the constant out and there's nothing left, it is just dx right there. It's like 1 dx technically. And now I can sub in what I know. I know that this is equal to 26 over 3. I've got a negative out front, so negative 26 over 3 plus 4 times the integral of x dx is 4. 4 times 4 minus 3 times 2. So negative 26 over 3 plus 16 is going to become 48 over 3. Minus 6 is going to become minus 18 over 3. Let's see, 48 minus 18 is 30 over 3. Negative 26 plus 30 is 4 over 3. Now, in the next day or two, we are going to be not using geometric values. We will just be using our integration rules that we know. But sometimes it is faster to just think about the actual area. So that's what this lesson was all about today.